In this lesson, we'll have another look at the shortest route or minimum path problem between two vertices. In our earlier work, we found this was fairly simple to do for small networks. However, it becomes increasingly more difficult as the network grows in size. For these larger networks, you need a systematic method called an algorithm to find the shortest path. A Dutch computer scientist, Dijkstra, developed an algorithm to determine the shortest path through a network. His algorithm and others have important applications to computerized routing and scheduling programs, such as the GPS navigation devices that lots of people use today. Let's have a look at the steps we need for Dijkstra's algorithm. It's an organized square array or table or matrix, and we generate this table using each vertex. The first element or starting row must correspond to the start vertex in the network we're interested in. Then we evaluate each vertex. The final table shows the shortest paths to all the other vertices from this start vertex. Each row of the table looks at the weight to the other vertices. A subscript is used to show which vertex the total weight was calculated from. If a vertex is not directly connected, the weight is considered as infinite. This algorithm is best shown by example, which we'll do next. In this problem, we're going to look at the shortest path and the route between town C and town F in the network. And then we can list the other points as they move away from C. In fact, the order of the other vertices doesn't matter. Now, when we're at C, we don't have to go anywhere to get to C, so the distance to C is 0. And we use the little subscript to represent the vertex we came from. Now, the distance from C to B is 5. So we use we use the subscript C to represent where we've come from, C to B. Now we look at C to D is 6. So that's 6 coming from C. Now there's no direct route to get to A from C, or E, or F. So those routes are marked as an infinite distance to show that. Now we look at the other values in the row other than the one we've boxed, and the smallest one is this one here, 5C. So it becomes the boxed value for the next row, and that next row came from column B, so we're going to now look at our routes from point B. Now there's no need to repeat anything under a boxed item because that is the minimum distance, so we go across to D. Now we have come via C and that's 5, so here we are at B. How far is it to D? Well, we have to add 5 more to this value 5, so that's 10. Now that's 10 via B. If I look above, the 6 is better, so it goes into our table because we always choose the smaller value on comparison. Now can we get from B to A? Yes, we can. So that's an additional 7. So 5 plus 7 is 12. And so now we use the subscript B to show that we came via B. 12 is obviously better than infinity. Can we get to E? Yes, we can. We had added an additional 4. So 5 plus 4 gives 9. And so that was via B, and that's definitely better than infinity. And can we get from B to F? Oh, well, we can't directly, so it stays as infinity. So the shortest unboxed value in this row is this one, and it comes from column D, so that's going to head up our next row. So we box 6C as our next best shortest route, and that's now looking at all the points from D. We don't need to do these again, they already have boxes in those columns, so we're looking at D to A. So from D to A, that one there, we add an additional 8, so 6 plus 8 is 14, 14 via D. But if we compare it to above, the 12B is better, so 12B goes into our row. Now we look at from D to E. So D to E is an additional 9. 6 plus 9 is 15, so 15 via D. Compare it to above. No, the above is better, so we keep that shorter distance from above. Can we get from D to F? Well, no, we can't do it directly, so it stays as infinite. Alright, so the next smallest value is this one, 9b, from column E. So it goes as our next box value in the row, and the row is now via E. So we've done this one, this one, and this one. They've all got highlights, box values. Let's look at E to A. Well, we can't get from E to A, so that's infinite. So 12b is better from above. Let's look at E to F. Can we get to F? Yes, we can. We have an additional 7. So 9 plus 7 is 16, and that's via E, and that's definitely better than infinity. Now, once again, we look at the unboxed values, and the best one is 12 via B. So it's in column A. It becomes our next row and our next boxed value. Alright, so there's only one more to check. That's A to F. A to F is an additional 6. 12 plus 6 is 18 via A, and you can see 16 is better, so we keep that one. And finally, we have this one is unboxed, and it's our best value. It goes into our final row, and of course that finishes all the points. So if we use this to find the shortest distance to town F, well, we start here, we work backwards, and you can see that from town F, we came from E, and then we go up here, and that came from B. We go up here and across, that's the best one, that came from C. So that shows the route that's best from C to F, and the distance of that route is 16 kilometers. Now, even though the problem asks us for the shortest route between C and F, we can use this table to work out the shortest route to any other point. So if we wanted to work out the shortest route from C to E, again we work backwards. Here's E, we go up, we came from B, and then to C. And so that would be the shortest route. If we want to find the distance, we can see it's highlighted as 9 kilometers. Why don't you test it out? We chose this example because it was an easy problem to do by inspection because it's a small network. Now carefully go over it again if you want to see the steps.